Hello everybody, myself Dr. Shweta Prakash, and I am from the Department of Applied Sciences, and I will be teaching you, giving a lecture on engineering physics. And our subject code for the engineering physics, as you can see, is KAS 101T, and this is a course in the AKTU engineering colleges. This is followed by this syllabus, okay? And I will be giving you lecture on relativistic mechanics. In our engineering physics course, this is the first topic, all right? That is the first unit which we are going to study. And in this unit, the whole relativistic mechanics, I will be basically talking about a topic which is named as addition of velocities, all right? So, these are the topics. First, I will give a brief introduction about the topics. So, firstly, we are having frames of references. In that, we are having inertial and non-inertial frames. Then we are having the Galilean transformation, all right, Michelson-Morley experiment, postulates of special theory of relativity, Lorentz transformations, so length contraction, time dilation, velocity addition theorem, and some other topics are variation of mass with velocity, Einstein's mass energy relation, relativistic relation between energy and momentum, and massless particles. So, this is the topics content which we are covering in this unit 1, relativistic mechanics. In this content, what happens, I will be talking about this velocity addition theorem, as you can see, all right. So, velocity addition theorem we will discuss. So, this is our topic, all right. It is also known as addition of velocities, all right. The theorem which is called as the velocity addition, it is also referred to as addition of velocities, all right. So, basically this theorem is applicable to a particular range of velocities. What happens in the relativistic mechanics, we divide the entire relativistic mechanics in two parts, all right. One is the classical mechanics, that is the classical or the general relativity, where we are basically discussing the relative motion of the particles which are moving with the velocity which is much less than the speed of light. So, those motions are coming in the general theory of relativity or in the general relativity. And then the other part, the other class of relativity is the relativistic mechanics, all right. So, in that is the special theory of relativity. So, in that theory, we are basically dealing with the motions which are having the velocities comparable to the speed of light. So, that is coming in the special theory of relativity. So, this velocity addition theorem which we are having here, that is basically dealing with those motions where the velocities are in the range which is comparable to the speed of light. This is shown like this, all right. So, V is nearly equal to C. So, you can see what is the meaning of the motions which are having the velocity which are comparable, all right. That is nearly, that is close to the speed of light, and all of us are familiar that the speed of light is represented by this C, all right. So, in order to discuss about this addition theorem, we need to define the motions, and to define the motions, we need to define the frames of references. So, from here our discussion is starting, all right. So, you can see that we will first define the two frames which are known as our S frame and S dash frame, all right. So, we must understand what are the properties of the S frame, why it is referred to as, all right. So, the S frame is our rest frame, all right. That frame will be rest frame, and the information which we will be giving in this frame, that information will be given in terms of the coordinates x, y, z, These will be the position coordinates, and the time information will be given by t. So, this is how we define, and this is what we mean when we say S frame. Whenever in the discussion we will say S frame, so it is referred to as the rest frame. We will understand that we are talking about the rest frame. Now, we will come to the definition of the S dash frame. How do we define the S dash frame? All right. So, now this S dash is a moving frame. All right. And how it is moving? It is not moving in any random direction. It is moving in the positive x direction. All right. And it is moving with the constant velocity v. All right. With respect to this rest frame S. So, this is how the S dash frame is defined. All right. And now how do we study the motions in the S dash frame? How do we give information when we are discussing the S dash frame? So, the information will be given in again terms of position coordinates as we had in the S frame, and the time coordinates again as we have in the S frame. But the difference is that since it is the S dash frame, the information about the positions will be in terms of dash coordinates. You can see x dash, y dash, z dash. And the time coordinate will be t dash. It will be represented by t dash. All right. So, this is how the S dash frame is going to give us the study. At different places, this dash frame or the dash coordinates are also given the name as prime coordinates. All right. So, these coordinates are also referred to as the prime coordinates. Now, what happens? Now, we have to establish a relation between these S and S dash. We must remember that we are going to study the relative motion. Whatever study we are going to make, that will be applied to the relative motion. All right. It is the relativistic mechanics is our unit. All right. So, now we relate the S dash frame and the S frame. Although we have already given the information that S dash is moving with constant velocity with respect to S frame, we must understand that what will happen with this constant velocity. The moment we say that S dash frame is moving with constant velocity with the S frame, it gives us the information that both the S and the S dash frame, they are inertial. All right. In some other lectures, you will be familiar exactly in detail that what is the meaning of the inertial frame, how do they behave. Okay. For these discussion, what happens? For entire discussion of the relativistic mechanics, we will be preferring the inertial frames. All right. Because as I said that there are two branches of the relativity, the general theory of relativity and the special theory of relativity. The laws which are given, the theorems which are already made, all right, the postulates which are given. So, they are given for the inertial frames. So, that is why whenever we define the frames, we will make sure that they are inertial. All right. Just to give a very short and a very brief idea to you all about the inertial frames, I would like to give you the idea that all those frames which will be following the law of inertia, they will be kept in the category of this inertial frames. All right. And I suppose all of us are familiar with this law of inertia. All right. So, up till here, our definition of the frames is complete. Now, we have defined the frames which will be helpful for us to study this addition of velocity. All right. So, now we go to our next step. What is our next step? Our next step is defining event. All right. So, what is event? Now, in the previous slide, in the previous discussion just now, you have seen that we have defined the frames. Why we have defined the frames? so that we can study the relative motion, and then we can move to the discussion of the velocity. So, for that we need to define an event, a motion, any activity which we define in the frames, that is termed as event. Any motion, suppose we say that a particle is moving in the frame S, a particle is moving in the frame S dash, so that will be our event. A particle is traveling a distance so and so, so that is an event. Two particles are colliding, two particles are moving towards each other, all those are events. So, we have to, in order to study any particular activity or theorem or phenomena, we need to define an event, all right. So, we define an event, just we will take a very simple event so that we can understand how the entire process of velocity is going on, how the frame is working. So, for that we just choose that an event may be a particle is moving, all right, with velocity u dash and in the S dash frame. Now, this is very important. When we define an event, we need to specify that in which frame we are defining in the event, all right. So, frame of references S and S dash, they are having a particular role. So, we need to specify that where the event is defined, all right. And also it is important to specify why it is important to specify. Suppose we have specified that a particle is moving with velocity u dash in the frame S dash. This is clear, all right. So, what will happen? This particle, the motion of this particle will become relative for the S frame by default, all right. We will come to this point, all right. So, what happens? Now, we have defined that the particle is moving with velocity u dash in the frame S dash. Now, we any person who is present in this frame S dash will observe this motion, and suppose that person is able to record the position of the particle at after some time t dash, and the person is able to record that at after some time t dash, the particle reaches at the position r dash from the origin o dash, again in the S dash frame, all right. So, this much information the person is giving in the S dash frame about the moving particle, all right. Then what happens? Now, we come to the point that this motion, this same motion is observed by the observer or the person who is present in the S frame. Let me also make this point clear that the person who is present in a frame is referred to as observer, all right. Person is present in the S frame, so that person is the observer for the S frame. Person is present in the S dash frame, that person will be observer for the S dash frame. So, the person who is present in S frame now is able to observe, let us say that the person is able to observe the motion which is done in the S dash frame. Now, we already have defined that S dash is in motion, all right. So, whatever activity will be taking place in this S dash will by default become relative to the person who is present in the S frame. So, that is why whatever event is happening here in the S dash frame will by default be relative to the S frame. This is how, by defining these S frame, S dash frame, the event, we define the problem of relativity. Now, whatever information this S frame observer is going to give us will be the study or the information of relativity. So, that is how the definition of the events and the frames of reference is playing the role in the relativity. All right. Now, let us see what observation this S frame observer is making. What he is saying? He is saying that the velocity for this same event, all right, we are not defining a new event. He is saying that the velocity of this moving particle is u. All right. Now, we have to be careful. The particle is moving with velocity u dash in this S dash frame. But the S frame observer is saying that the particle is moving with u velocity. All right. It is very essential to point out that we cannot take u dash here. All right. The S frame coordinates cannot be written in dash terms. They are not having any coordinate of dash, all right, or prime. And he is saying that the particle is at position what? R in place of R dash. All right. So, this much information this S frame observer is able to make. All right. So, now what happens? Now comes the role of relative study. All right. So, how does this relative study take place? When we find out the relation between u and u dash. U is the velocity measured in the S frame and u dash is the velocity measured in the S dash frame. Therefore, our next step will be to find out a relation between u and u dash. Let us see how do we do it. All right. All right. Before that, while I was talking about the frame of references, let me show you with the help of this figure that how the frame of references are designed, how do they behave, how do they work, how do they help us in studying relativity. So, we will first look at this part, this S frame. And we will be able to understand that this S frame is the rest frame. We have already defined it. It is the rest frame. All right. And you are able to see that to define the frame of references, we have taken the help of Cartesian coordinate system because this is the most familiar coordinate system which we know. And all the laws, all the properties we are familiar. So, we will be able to develop the laws with the help of these Cartesian coordinate system very easily. So, this is the S frame. All right. Now, we come to this S dash frame. All right. So, this S dash frame is again I am reminding you that S dash frame was our moving frame. All right, and it was moving with some constant velocity v. All right, I hope you are able to understand that the velocity v is constant. All right, and the direction itself is showing that the velocity, that the frame is moving in positive x direction. All right, if you look at the direction, you are familiar. All right, and we must keep in mind that the velocity has to be constant because we need inertial frames. The moment the velocity becomes constant, we are having both the frames as inertial frames. All right. So, this is about the S dash frame. Now, we come to the event which is defined in the S dash frame. What event we have defined? We have defined that a particle is moving with velocity u dash in the S dash frame. Now, you can see that this part O dash P, let us say, is the point where the particle has reached after a time t dash. So, the particle has travelled a distance O dash P and this distance is given by R dash. All right. and this part of discussion is in the S dash frame. And if we want to find out the position of the particle, then it can be in terms of x dash, y dash and the z dash coordinates and the t dash time. All right. So, this part is in the S dash frame. Now, what happens? Now, we come to this S frame. We were talking that whatever thing will be defined in the S dash frame, that will be observed by this S frame observer, isn't it? So, this person is observing. How the person observes, you can see. The person is saying that this particle, the same particle which is present at P has traveled a distance R, all right, according to this frame, S frame. And what else the person is saying? The person is saying that in time T, this frame S dash has traveled a distance how much? Vt. V was the velocity of this S dash and T is the time. So, this observer is saying that in time T, the frame S dash has traveled a distance Vt in the positive x direction. Now, what else the information is taken from by the S frame observer? The observer is saying that the position of this coordinate P, all right, this point P is in terms of x, y, z and the time coordinate T. So, all these informations the S frame observer is going to give. So, I think with the help of this diagram, it is clear how the frames are working, how the frames are going to be used, all right, further. So, now after this discussion, we must move to the velocity part, since our topic is the velocity addition. So, now we must use the discussion to calculate the velocity of the particle in both the frames and hence find the relation between these velocities. And let us see what do we get. So, first of all, we write down the velocity for the particle in the S frame, as you can see, and the velocities are calculated in the directions x, y and z, all right, so that we are able to study the different components of velocity and hence find the relation between these components separately, all right. So, in the x direction, how do we write down this velocity? Ux, all right, x is showing the component in the x direction. So, we all know that the velocity is the differentiation of the position with respect to time. So, that is the thing which is done here, dx by dt is done here, all right. So, because x is the displacement or the position in the x direction and time happens to be there, all right. So, ux is equals to dx by dt, all right. We have to find out the value for this, then only we will get the value of the velocity component. So, you can see in the next step, we are having what? We are having this ux and is equals to dx by dt, all right. And next step you must see that what we have done. Now, what happens? This x coordinate, all right, it has no term. We will see in the further steps that this x component, it has no term of time t. However, it has the term t dash, all right. The x component does not have any variable of time t. It has in place, it has a variable of time t dash. So, therefore, we have to break this part dx by dt and write it as dx by dt dash, all right. And then we have to further differentiate this dt dash with respect to t. This type of differentiation is done when we are having one variable in terms of the other, all right. So, this type of differentiation is done. So we will use this differentiation. Now what happens? Now we will find out, now we will use the x coordinate. So how do we use the x coordinate? We write down the transformation. What transformation we are using here is the Lorentz transformation. In fact, the inverse of the Lorentz transformation we are using, and inverse of the Lorentz transformation is this x. For the x coordinate, it is x dash plus vt dash upon square root of 1 minus v square by c square. This is for x component. For y, it is simply y dash. For z, it is again simply z dash. For time, again, it is showing t dash plus vx dash by c square, and then upon square root of 1 minus v square by c square. All right. So these equations x, y, z and t, these expressions, these equations are the inverse Lorentz transformation, and we are going to use these transformations step by step in order to calculate the velocity. As you can see, we are calculating the x component of the velocity. So we will require this x part, this part, x dash plus vt dash upon 1 minus v square by c square square root. So, and we differentiate this dx by dt dash. You can see that we have to do this part first, this dx by dt dash part. All right. So, what is going to happen? All right, this part, we have to do this part first. All right, we are doing this part, and for that we have chosen dx by dt dash, and you can see that this x is having x dash variable and t dash. It is not having t variable. All right, for the same reason we have written this. So when we are doing the differentiation, we are having in the first term dx dash by dt dash plus v, and then dt dash by dt, this term. All right, and then 1 minus v square by c square square root has to be as it is. Because why? Because v is constant. So because v is what? V is the velocity with which the s dash frame is moving. So that velocity has to be constant. So it cannot have a time derivative. So that is why this factor 1 minus v square by c square square root is as it is. So what happens to this dx dash by dt dash? It becomes ux dash. It is obvious because x dash is the x component of the displacement in the s dash frame, and t dash is the again in the time in the s dash frame. So when we are having the derivative, they will give the velocity in the s dash frame. So that is why ux dash plus v, because this dt dash by dt dash will be equal to what? 1. So plus v, and again this part remains as it is. All right. So this is how we get our first equation, where we are solving this dx by dt dash is equals to ux dash plus v upon 1 minus v square by c square square root. This will be giving us this part. All right. Now we are going to work for this second part, dt dash by dt. All right. So now what happens? For that, for this part, we are going to use this time transformation. All right. So what is the time transformation? T dash plus Vx dash upon c square upon 1 minus v square by c square square root. All right. So this is having this t dash term. So what do? We just find out the derivative dt by dt dash here. All right. We start differentiating this whole part with respect to t dash. So when we do it, so we are having dt dash by dt dash here plus v, and this is dx dash by dt dash and then oblique c square, where nothing is going to happen to v, nothing is going to happen with c. The reason we have already discussed, c is the velocity of light, hence it is constant, and v is the constant velocity with which the frame S dash is moving. And the same reason will be for the denominator, 1 minus v square by c square square root. So what happens to this dt dash by dt dash? 1. So 1 is here, plus this v is as it is, we can see here, and then this dx dash by dt dash is ux dash by c square, and then 1 minus v square by c square square root. So this is our equation 2, equation 1, all right. So with the equation 2, I think we have completed the discussion for ux, all right, rather calculation for ux. So now we must see that how is the expression for ux. All right, using equation 1 and 2, that is, we have discussed that ux is equals to dx by dt dash and dt dash by dt. So we will substitute those values 1 and 2, and then we will have the value of ux. How do we have the value of ux? It is ux dash plus v upon 1 plus ux dash v by c square. So this is the x component of the velocity in the S frame, all right, as observed by the observer. All right. So this equation is giving the x component of velocity. So if we look at this equation 3, up till now we have established a relation between the x component of the velocity in the S frame and in the dash frame, because dash frame velocity x component is this ux dash, all right. Now we have to do for the y component. I have already discussed, we will be evaluating the components separately, all right. So for the y component, now we have to do the calculation. Now first of all, we will write down the y component of the velocity in the S frame, and let us see what is it. It is uy is equals to dy by dt. This is a normal, a general and the standard definition of velocity, differentiation of the position with respect to time. So by that, this is uy is dy by dt, all right. Again the same problem. What problem is here now? Problem is this, that the y part, all right, it is having no variable of t, all right. So again we have to follow the same process, the dash process. It will be having a dependence on the dash variable. So that is why we again write dy by dt in terms of what? Dy by dt dash. Again we have to, for the elimination of this dt dash, we have to evaluate dt dash by dt, all right. Again the same process as we have done in x. So this is how we will be able to get the y component of the velocity, all right. So let us see now what according to the inverse Lorentz transformation is the value of the y part or the y variable. So the inverse Lorentz transformation says y is equal to y dash, all right. We substitute for this y is equals to y dash here, and we calculate dy by dt dash. This is simply dy dash by dt dash and is equals to, what will happen to this dy dash by dt dash? Both are the S dash frame variables, so they will give a term which is the S dash frame property. So they will give a term uy dash, all right. So this part is done. Now this part dt dash by dt is already the same, because nothing is going to change here, all right. If there is any confusion, you can go back and just see this. Here for the x component we had this term dt dash by dt, all right. There is no x part attached to this, so it has nothing to do with x, y, z. It will, whenever it will come in the calculation, it will be the same, all right. So once we have evaluated this, we can use this part as it is. So that's what we are going to do here. All right. We are going to use that part, this dt dash by dt as it is from the previous calculation. All right. So what do? We just put that calculation here, dt dash by dt part here. And for dy by dt dash, we have already uy dash. So this is uy and this becomes uy, and this is equal to uy dash 1 minus v square by c square. This c square is missing here. All right. So 1 minus v square by c square square root and upon 1 plus ux dash v by c square. All right. So this is our equation 4, and this is our component of velocity in the y direction in the S frame. So this is how we completely define what is this part. All right. So we have calculated x here by equation 3, we have calculated y by equation 4. Now we have to go to the z component of the velocity. All right. Now what happens? The z component we will see when we will evaluate. We will see that the z component is very much familiar with the y component, isn't it? So what do? That we first of all write down this component of the velocity in the z direction, and that is uz. It is given by uz for the S frame, and again it will be the differentiation of the position with respect to time. So that will give us dz by dt. Again the same concept. It is not going to have the prime coordinate or the dash coordinate, the unprime coordinate. That means t. It is not going to have t. All right. Every time when I am saying that it is not going to have t, it is not going to have, it is not a function, then you can go back and confirm where we are having the inverse Lorentz transformation, isn't it? You can see that x is this expression and it is not having term t. It is not a function of t. You can see y, it is not a function of t. You can see z, it is not a function of t. All right. So for this purpose, we are forced to write down this velocity in terms of these dash parts also. So that is why this dz by dt will be dz by dt dash, as you already have done in x and y, and again dt dash by dt. All right. Again, we will use this inverse Lorentz transformation, and we will see that what the transformation is saying about the z coordinate. All right. It is saying z equals to z dash. So we will substitute this value for the uz, and we will evaluate this part dz by dt dash, because this dt dash by dt will be same starting from the x part. So dz by dt dash we substitute and we get dz dash by dt dash, and we are having this as uz dash. All right. Dz dash by dt dash is known as uz dash. It can be defined, it can be termed as uz dash. All right. Now, with the help of all the values, that means this value uz dash and the value of dt dash by dt, we write down the z component of velocity for the S frame. And when we write down, then what is it? uz is equals to uz dash 1 minus again v square by c square. Please see that in the square root, inside the square root, we are having the complete factor 1 minus v square by c square, square root upon 1 plus ux dash v by c square. All right. So this happens to be our equation 5, and our last component of velocity, that means ux, uy and uz, these components of velocity we have to find out. So this z is the last component. All right. Now what happens? Now we again recall that what are the components of velocity which we have calculated in different directions x, y, z. Okay, so the components are ux is equals to ux dash plus v upon 1 plus ux dash v by c square. Again, the component of this uy is uy dash 1 minus v square by c square square root upon 1 plus ux dash by ux dash v by c square, and this uz is uz dash into 1 minus v square by c square square root upon 1 plus ux dash v by c square. So these three, all right, these three are the component of velocities in the S frame, all right, and all of them are related to the S dash frame components. These x dash, y dash, z dash, these are the dash frame components of velocity. All right. Now, if we look at these three values, we can see that this x part is behaving differently. All right. It is having one expression which is ux dash plus v, whereas this kind of expression is not present in y component and it is also not present in the z component. All right. So we have to think about it. All right. So what is so special in the x part? All right. So although we have calculated, we have used the same phenomena for all the three directions, but how come that this x part is having this difference apart from y and z? So the difference lies in the relative motion. If we remember, when we defined the frame, all right, we have said that S frame is a rest frame, but the S dash frame is moving. And not only it is in motion, it is in motion in one particular direction, and that is the positive x direction. And it is moving with constant velocity v. So this was the complete definition of the S dash frame. So what happens, just because it is moving in this positive x direction, the relative effect, all right, the relative motion, the relative changes, all right, in different things are only observable in the x direction, whereas there is no effect of relative motion which is observed in the y and the z direction. So this ux dash plus v is showing that the motion is along the positive x direction and not along the y and the z direction. If the motion had been in the y or the z direction, the same change would have been observed in these y or z, and whereas there would have been no change in the x direction. All right. So this point is very important, that we need to be very sure about the direction of the motion of the frame of the body, in which direction the motion is taking place. In that direction only the relative effect will be observed, while the other directions will not show the effect of relativity. Definitely they will transform. It is not that they will not transform. They will transform, but they will not transform in the way that x component is transforming. They will not transform in the manner in which the x component is transforming. So that is the difference in the direction in which the motion is taking place. All right. So this is a big point in the relativity. All right. So this is what need to be observed from here. So from these equations 3, 4 and 5, we can see how we can calculate these velocity components independently, how we can relate the velocity components of S and S dash frame independently. All right, the X, if we want to study about the relation between the X component of the S frame and the S dash frame, we can choose this third equation. If we want to study the relation between the Y component of the motions in the two frames, so we can choose the equation 4. If we want to study the Z component, so we can choose the equation 5. All right. So now what happens? We can also combine these equations. We can also combine these equations and develop a universal equation which will represent all these three equations, all right, in components. So how do we combine? We combine them in terms of vector. All right, suppose we write down the velocity vector u, all right, for the S frame. So u can be written as uxi for the x component, plus uyj for the y component, plus uzk for the z component. This vector form everybody is familiar, all right. So we can understand that if we combine those equations ux, uy and uz, so we can combine and we can form a vector and we can write these in the vector form. All right. And then we can analyze different situations. We can see what is going to happen if the motion is along one direction. Like if we say that the particle in the S dash frame is having component of velocity only in the x direction. All right. If we have understood that the frame is moving in positive x direction. Now inside the frame, the particle is moving. So what will happen if that particle is having only component in x direction? It means that the particle is traveling in the x direction. All right. It is not showing any motion in the y and the z. So what happens? So this activity is observed in the S dash frame. So for the S dash frame, this uy dash, the y component of the velocity of the particle, it goes to 0. It vanishes. It has no meaning. So, and the z component uz dash, it also goes to 0. It again has no meaning. All right. So then what happens if we put these values, all right? If we put these values here, if we put this value u dash, uy dash equal to 0, all right, uy dash equal to 0 here, and then uz dash equal to 0 here, this part, that is what the case we are discussing. So what happens to uz? Suppose we put uz dash is equals to 0, so what happens to uz? So it goes to 0. So uy dash we substitute, so what happens to uy? It also goes to 0. All right. So ux we have no information, only information that it is traveling in the x direction. All right. So uy dash is equals to 0 and uz dash equals to 0. Substituting these values, we are having ux, uy and uz 0 here. So now look at this part. U is equals to ux only, isn't it? From this part. If we put the value of uy and uz as we have discussed in this equation 6, so then this is equal to हाँ मेरा अभी ये लास्ट है हाँ कोई नहीं इसे कंप्लीट कर लीजिए ना okay so we substitute for this all right so this becomes u is equals to ux if we do this all right so when we have this u equals to ux so we can substitute the value of ux all right so I hope you remember this ux is here so this becomes the value of u now all right so what do? We substitute ux, all right. So this is u in place of ux. In place of ux dash, we had u dash. So this is u dash. So this is u is equals to u dash plus v upon 1 plus u dash v by c square. All right. So this equation is basically known as the relativistic law of addition of velocity or the velocity addition theorem. All right. So this is the standard form of this equation, this theorem. All right. So next what happens? Now we can look at the classical picture of this theorem. If you remember, we had put a condition on this v in the starting. We had said that we will be working for this part, v is nearly equal to c. All right. Now we say that working at this part, we can look at the classical picture also. So classical picture means where the velocity is much smaller than c. That is the classical picture. So the moment we look at the classical picture, this is v much smaller than c is substituted here. So this whole thing becomes much smaller than 1. And we can neglect this whole part and we can simply have this u is equals to u dash plus v. All right. So this is the classical relation and it was initially given by Galilean. All right. So Galilean basically developed these transformations which were applicable for the classical region only in this velocity range. They did not work when we use the transformation for this range. The Galilean part does not work. So that is why we required a new velocity transformation and that is why the study started for this. And we were having that transformation which we have this equation 7. All right. So what happens now? We see that how this new transformation works for the velocity of light. You can see that as soon as we say that u dash is equals to c, so we substitute here and how u dash is equals to c is giving us the result u equal to c, which is very normal. If an object is moving with velocity of light, so we expect that it should have the same velocity whatever changes. All right. So object is moving with velocity of light in the s dash frame. All right. So if we use the velocity addition theorem, we are getting the same velocity for the s frame. So that is how the velocity addition theorem is supporting the fact that the speed of light is constant. Moreover, this fact was given as a postulate in the special theory of relativity by Einstein. He has said that the speed of light remains constant at a value of 2.99 into 10 to the power of 8 meter per second in all inertial frames. So we can see that the velocity transformation is supporting the Einstein's second postulate. All right, we can see that also. So that is the importance and the significance of this velocity transformation. Then we are having some numerical problems which you can see. That means two particles come toward each other, all right, each with a speed of 0.9 c. With respect to the laboratory, what is their relative speed? That is the question. And in this question, what happens? The speed of the two particles are in reference to a fixed point in the frame. We have to choose a fixed point and we have to take one particle as the reference point and then the other particle will be moving in the reverse direction with the same speed. So we will have the value v as 0.9 c and u dash as 0.9 c. Therefore, now we will substitute in the velocity addition theorem, all right, and we will get the value of u as 0.995 c. So we will be able to find out the relative speed of the particles with respect to each other. So these are some numericals, all right. And then this is another numerical. Spacecraft alpha is moving at 0.9 c with respect to the Earth. If the spacecraft beta is to pass alpha at a relative speed of 0.5 c in the same direction, what speed must beta have with respect to the Earth? So in this solution, it is very clear that spacecraft alpha is our S dash frame, all right, because it is moving. and the velocity of alpha is 0.90 c. So this is v, and the spacecraft beta is the object which is moving inside the alpha. So it is the moving particle which we used to refer in the S dash frame. So its velocity will be termed as u dash is equals to 0.5 c. And then we need to know the velocity of the beta with respect to Earth. So that is clear, Earth is our rest frame, and the velocity of beta with respect to Earth will be u, and we use this formula u dash plus v upon 1 plus u dash v by c squared. So this is the part, calculation part, and you can see for yourself if you calculate that you will have this value. All right. So these are small numericals. We can have a large number of numericals on this, and we can understand the concept by using these numericals. That is all for this lecture, addition of velocity. For any reference, you can go through these reference books also. All right. So that is all for this lecture. Thank you.